Greetings and welcome. Today we'll be looking at Lewis structures and covalent bonding. This will be the first real video of the semester and indeed of the entire year of organic chemistry. So I invite you to remember that you can pause this, rewind it, certainly take some notes. So I would suggest you get out some paper and have a pencil handy to not only take notes but also to work out some problems as we go along. All right, let's jump right in. To begin with, what we'll need to do is look at the periodic table. In your classroom, what you'll see is that there's a periodic table that looks just like this one. We can see that along the right corner here, to right top corner, this is what we'll be using mostly in this class. Boron, carbon, nitrogen, oxygen, and the halogens, and also hydrogen, which is located way up here. All of the metals, which is all of this guy, right in here. We're not going to use that very much, so what I'm going to do is just give you a little blow up of the parts of the periodic table that we'll be using the most. So with this expanded partial periodic table, we can see pretty much everything that we need. You may recall from general chemistry, but I will review it right now, something that is incredibly important and crucial to your ability to do everything in this class, which is to draw Lewis structures, and that's what we will be working on today. So Lewis structures involve, again, mostly carbon, nitrogen, oxygen, the halogens in general, which we usually abbreviate as just X, and then hydrogen up here. The column in which you find these elements in the periodic table, so column number 1, column number 3, 4, 5, 6, 7, etc., indicate how many valence electrons each of these have. So, with valence electrons, what we do is put one dot around each of these to indicate how many valence electrons they have for the Lewis dot structure. So for instance, hydrogen has one valence electron. It's in column 1. So we would just put one valence electron or one dot right next to hydrogen. Carbon is in column 4. So carbon has 4 valence electrons around it. And we would space them out into the possible sides of it. So we've got one on the top, one on the bottom, one on the right, and one on the left. So that's the 4 valence electrons around carbon. Again, that comes from the indicator up here that this is in column number 4. And so carbon has 4 valence electrons. Nitrogen would have 5 because it's in column 5. So what we would do with nitrogen is put one on each side. And that only gives us 4 because there's only 4 sides around this thing. So instead of having another unpaired electron somewhere else kind of spread out star shape, what we would do is we would start pairing them up. So the 5th electron now basically has to share a bedroom. It doesn't matter which side you put it on, but essentially that leaves nitrogen with 3 unpaired electrons and 1 pair of electrons. Right? Likewise, when we move into oxygen, oxygen would have 6 valence electrons. So we would start off spreading them out first, 1, 2, 3, 4, and then we would put number 5 and number 6 paired up. So oxygen would only have 2 unpaired electrons and 2 pairs. Lastly, halogens. Halogens, again, I'm just going to put an X, but fluorine and chlorine and bromine and iodine would all act the same way. They have 7 valence electrons. Again, you don't need to memorize that. You'll always have the periodic table available to you. And you can see that they're in column number 7, and therefore they have 7 valence electrons. We would fill them in one at a time. 1, 2, 3, 4, 5, 6, 7. All right, therefore, halogens would have 1 unpaired electron and 3 pairs, what we call lone pairs of electrons. So, when we start to build Lewis structures, what's first important is to understand how many valence electrons each of these guys have, which tells us how many bonds they're going to need to make. Each of these 4 elements on the right, carbon, nitrogen, oxygen, and the halogens in general, always need to fulfill the octet rule if they can. The octet rule is to have 8 electrons around them. Notice that none of them by themselves have 8 electrons around them. Therefore, they need to share electrons. Carbon would need to share or gain an extra electron on each side in order to have 2, 4, 6, and 8. And that's what covalent means. So a covalent bond is that you're sharing electrons. So for instance, carbon and hydrogen could get together and share those electrons. We would have 2 electrons in between that hydrogen and the carbon. And you could see that at this point, the hydrogen would have 2 electrons, and carbon would be closer to having all of its electrons. If carbon made covalent bonds with 4 different hydrogens, and each of those hydrogens brought an electron with it, we can see what kind of looks like a Venn diagram with 5 overlapping spheres or circles. And now carbon would have a share of 8 electrons, therefore fulfilling its octet rule, and each of those hydrogens would have a pair of electrons, and that's all that hydrogen wants. So we would do this with nitrogen and oxygen and halogen, and end up making Lewis structures in which each of these guys, carbon, nitrogen, oxygen, and halogen, each has 8 electrons. So let's work some examples. First, I'm going to include that partial periodic table again. And let's look at a few different possibilities. All right, so we already did CH4. So CH4 would be a structure in which we have a carbon, and then we would fill it in with 4 hydrogens around it. And each of those would bring 1 more electron, and therefore we would have filled the octet of CH4. Usually what we'll do is write that with a dash instead of a pair of electrons. In fact, it's really good to get in the habit of just doing the dashes. This will become much easier very quickly, or it needs to, because we're going to be doing Lewis structures for everything we write out. Every structure is going to be a Lewis structure that we're going to do in this class. All right, so let's move on to a structure NH3. So what you've probably noticed already is that the hydrogens, because they only form 1 bond, they only have 1 electron to share, are always around the outside. So I would always worry about the hydrogens last. So if we're worrying about the hydrogens last in NH3, the only other thing to worry about would be nitrogen. And nitrogen has 5 electrons, right? Notice it's right here in column number 5. And therefore, we would put 1, 2, 3, 4, and we just need to pair something up. And I'll pair it up on the right because it really doesn't matter. But notice that at this point, what we have is 4 unpaired electrons, 1 at the top, 1 at the left, and 1 at the bottom. I'm sorry, I think I said 4. 3 unpaired electrons. 1, 2, 3. That was a test to see if you're paying attention. So we have 3 spots in which we need to make a bond in order to satisfy its octet. And therefore, we need to bring in 1 hydrogen on each of those sides. And those electrons would make our 3 bonds. Therefore, the structure for this, the Lewis structure, could look like that. You could also draw the lone pair on the top, or the right, or the bottom. It doesn't really matter, so long as it has a lone pair on one side and 3 bonds to hydrogens on the other sides. All right, let's do one that's slightly more complicated, which would be C2H6O. All right, in this case, again, let's save the hydrogens for last and just worry about the carbons and the oxygens. So we have 2 carbons, each of which wants to make 4 bonds because they have 4 unpaired electrons, and 1 oxygen, which has 6 valence electrons, and therefore that guy wants to make 2 bonds because it has 2 unpaired electrons. So the carbons and the oxygen will be at the center of this molecule because by default the only thing left, the hydrogens, will be on the outside. So we can put this together in a couple different ways. Well, first off, we could just make a bond right here between these 2 carbons, sharing those electrons, make a bond right here between the carbon and the oxygen, and then what's left are 5 different spots on the carbons, 1, 2, 3, 4, 5, where we need to share some electrons, and 1 spot on the oxygen where we need to share some electrons. So therefore, we could just fill in our hydrogens around that. All right, and then we can pair these up. There's a pair, 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 a pair, and a pair. And at this point, we would have fulfilled everybody's octet, or at least the oxygen and the carbon's octets, and all of the hydrogens would be making a bond, and we would have a brand new Lewis structure that looks like this. All right. There is, however, another way to do this. C2H6O doesn't tell you in what order to arrange any of these things. So if we just think about the carbons and the oxygens, you can arrange them in 3 different possible structures. We could put carbon, carbon, oxygen from left to right, which is what we just did, carbon, carbon, oxygen. We could completely reverse it and do oxygen on the left and then carbon, although that would actually end up being the exact same molecule, just turned around backwards. Or you could put the two carbons on the outsides and the oxygen in the middle. Right? And that would let us, again, make bonds between carbon and oxygen, which need to be hooked up. And then you'll see that we have 6 spots to fill in hydrogens. 3 on each of the outside carbons. And the oxygen itself is already filled. Therefore, we would be done. We could write this one out as C with 3 H's on the left, and then an oxygen in the middle, and C with 3 H's on the right. And that would be a way to draw this molecule. So let's see if you've got this and you can kind of look at some structures and see which ones are good and which ones aren't quite right. All right, so let's move into something a little bit new, which is that sometimes you don't quite have the right number of atoms in order to make a molecule. So sometimes there's no way around this. So for example, you can't make something that's CH6. If you look at that, we've got carbon that has 4 spots to make bonds to, in this case, hydrogen. You can't put 6 hydrogens around that and have it all attached together. Again, the hydrogens need to be on the outside. If you try to put 2 hydrogens together and then 4 hydrogens on this guy, you would end up making CH4 and then just an H2 molecule, and those guys aren't attached together. So that would be impossible. All right, so I'm just going to strike that one out. If you wrote that down, maybe just erase it. But that's impossible, and there are always going to be things that are impossible. So you can't just randomly make up a string of letters and have it work. However, there are some cases in which we can make things work. So for instance, if you don't have enough hydrogens, there are a couple things that we can do. So let's do C2H4. Right? So if we draw out these 2 carbons, 1, 2, you'll notice that we can make that bond in between the 2 carbons and bond those together. And then if we try to fill in our hydrogens around the outside, we have 1, 2, 3, 4, 5, 6 spots for hydrogens. But we don't have 6 hydrogens, we only have 4. So what we can do is fill in our 4 hydrogens. 1, 2, 3, 4. And then we can just kind of circle those pairs. And what's left is 2 unpaired electrons, 1 on each of the carbons. Well, what we can do is we can bond those together as well. Just like we made a bond right here in between the 2 carbons to make a single bond, if you bond another pair of electrons together, 1 from each side, we can make a double bond. Hopefully you remember this from general chemistry. And that will let us make a molecule that does, again, have all of its octets filled, because each of these carbons has a share of 8 electrons. Right? There's 2 in the bond to the top left, 2 in the bottom to the bonds to the bottom left, and 4 in the center, and that makes 8. So each of those carbons has its octet filled, and that would be a double bond. So what happens is if you don't have enough hydrogens to go around, you have to make a double bond. It's also possible to make a triple bond. So in the example of a molecule that is HCN, and in this case I've arranged it linearly so that it works out right. So often you would write that as CHN, usually we write the carbons first. But when the H comes first it indicates to you that the molecule is acidic, and secondly, oftentimes when you have a couple in a row, it tells you in what order they go. So let's draw out our carbon. It has 4 unpaired electrons, therefore it needs to make 4 bonds. A nitrogen that has 3 unpaired electrons, so it needs to make 3 bonds. And then we have a hydrogen. Let's put the hydrogen on the left, and the best way to know this at this point is just because that's how we wrote this out, H and then C and then N. So we can make a bond between carbon and nitrogen, but then we don't have anything to fulfill those other bond spots, those other unpaired electrons, 1, 2, 3, 4. So we can make a double bond or a second bond between carbon and nitrogen, but we still have unpaired electrons, so we can make a triple bond or a third bond between carbon and nitrogen. And that would fulfill everyone's octet and give us an actual molecule. All right, so I've got one problem for you to try, and then we will come back together. So lastly, I just want to talk to you a little bit about kind of summarizing this and what I expect you to do before next class. So in terms of summarizing this, what we've noticed is that H always makes one bond. Carbon always makes 4 bonds. Nitrogen always makes 3, and oxygen always makes 2. Halogens, when we get back to those guys, halogens, because they had those 7 electrons, also end up, just like hydrogen, only making 1 bond. So then when you see something like, for instance, I don't know, CnH5, instead of having to draw all of the dots, what's much more common for practiced organic chemists, which you should hopefully be soon, is to draw out a carbon with 5 bonds, and then figure out, well, that needs to be next to our nitrogen, so I'll put a nitrogen at the end of one of those bonds. Nitrogen needs 3 bonds total, so we already have 1 at the left. We'll just make 2 more and fill in lone pairs. And then we have, at this point, 1, 2, 3, 4, 5 slots for hydrogen, and we can just fill them in. So instead of just doing the unpaired dots, we can instead just draw bonds, and that ends up kind of making this a little bit more simple. So that's something that I would like you guys to try to practice. So just kind of giving you a note going forward in this class. I will every day, or every video, post problems afterwards that I would like you guys to try. Ideally, what you will do is practice these before class. If you do that, then when you come to class and we're working problems, you can ask me any questions that you have. If you haven't practiced these, you'll come into class and practice for the first time. And when you do that, you may or may not be able to figure out exactly where you need help, and you might need to come back to me later. That's fine. I have office hours. I'm always happy to help you. But the best use of our time together in class is if you already know where you're struggling or what's working really well, I will help you in class, and I'm sure other people will have the exact same questions, to fill in your knowledge gaps. And that's why we're doing the class this way, so that we can work together to make sure in class that you've completed your knowledge and understand the skills going forwards. So thank you very much, and I will see you in class.